Last week we talked about SIFT. SIFT is try to find corresponding point. And when we talk about stereo is also try to find corresponding point. Okay, but stereo is try to find the corresponding point along a scale line. Right? So along the equipolar line. So stereo, we try to find corresponding point. We try to reduce 2D search to be 1D search. For the SIFT, is for two image. We try to find the corresponding point. This meaning in image 1, we select some good feature. In image 2, we select some good features. So different good features. So suppose in image 1, we have 100 good features. In image 2, we have probably 150 good features. So we pair 100 times 150. And we try to find corresponding point. And there are different methods because to find the corresponding, we have a pair, but how can we faster to find a corresponding point? Okay, there are different methods, but all are basic use SIFT. And right now, so those are kind of detection, and then probably we appropriate become the tracking. And right now, real tracking is this one, feature point tracking. We're doing before we do detect, select the good feature and do the detection. And right now, we try to do the tracking. Detection, tracking, and recognition. Okay. What's difference between the detection and tracking? Okay. Detection basically is try to search, try to find a template of try to find the target you need over entire image. That's detection. Detection, you support a template. Right, and use the NCC, use SAD, and you try to find corresponding page. But if you search the entire image. For the tracking, you only need to search a small region. So tracking will be much faster than the detection. That's tracking. Some people say detection equal to tracking equal to detection. That's incorrect. Even though some professors say, okay, we are doing because right now the detection is the detection very fast, so we don't need the tracking. No, we still need a tracking because tracking will be much faster than the detection because it needs to select to search a small region. So tracking, in order to find the target in next frame, in order to search a small region, we need to do prediction. So tracking will include prediction between two frames. Detection, you don't need to do prediction. If you are a mechanical engineer, you will find many people use the common filter. Common filter is one kind of a prediction. So if you are a mechanical engineer, many people use the common filter. And for the computer science or EE, or for the computer vision, people sometimes use we call particle filter. So particle filter and the common filter, both are competitors. Different method, but all do the prediction. And here I try to teach you one method we call optical flow. This one. Okay, but it's only for small page. For small page, like 11 by 11 small page. But if your target is bigger, you don't need to use optical flow. You should use like a particle filter. I don't teach particle filter because a little bit complicated here, but I teach you the optical flow. And the other purpose I'm trying to teach you the optical flow is trying to teach you the optimization method. For the calibration, I already teach you the closed-form solution, pseudo-inverse, and Devenberger-Manguan. Okay, this is for the optimization. But here I want to teach you one more optimization method. Is Taylor expansion. And the final one, the optimization method is the singular value decomposition. So actually, optimization we don't need to have many methods. I say again. So for the optimization process, actually what we did is that we teach you closed form solution. Right? Ax equal to 0 as closed form solution. Ax equal to b. Try to find x as pseudo inverse. But both are the first derivative. And a better approach, okay, we'll use this is a LM for a second derivative. That's one method. Okay. And the other group is here I want to teach you is that the Taylor expansion. Taylor 展开式 this year, this one. Okay. And Taylor expansion is very similar to gradient descent. It's kind of gradient descent method. That's it, what you did for the deep learning. And the third method, I'm going to teach you is use the PCA, but it's actually a singular value decomposition. It's eigenvalue, eigenvector. So actually, even me, until I work on computer vision, almost 30 years. Okay, I only use this three groups of 3 kinds of optimization method. 我只用这3个方法，没有用到太，就其他方法几乎都没用到，不是几乎我都没有用到啊。我们再回到这一边。So for the find a corresponding point, corresponding page, many people use the template matching, a small page. Okay. So we use the zero order. That means we use the texture. The raw data we call raw data. Is the data raw data. That's called zero order. And second method is the first order, first derivative. That's edge. That's kind of edge detection things. So it's a gradient component. Okay. So that's a optical flow is the first order. It's gradient component. And for the template matching, it's not easy to find it's not easy to find a subpixel accuracy. But optical flow can find the subpixel accuracy. Okay. And I just talk about the optimization. And here I also want to mention about Hessian matrix. When we talk about SIFT, I already teach you the Hessian matrix. But here I want to mention you again the Hessian matrix because Hessian matrix is important. Not only with last time we talked about is a good feature, it's corner or edge. But here, Hessian matrix also can let you what's the actual aperture problems. Aperture problem I teach you later is about optical flow things. The second is a good feature is a texture or textureless. Is it good texture or is it not a good texture? And third is uncertainty, 不确定性. Stable and unstable, we can judge by Hessian matrix. Keep talking. And I skip. Those are the basic I already talked about this one. And for the any 2D things, okay, actually sometimes you think about 3D model, 3D things. So I mentioned here. Okay. So that's why I just talked about the optimization method. So all those are optimization method. And even though Lagrange deep learning also apply Lagrange method. Okay, we start talking about what's tracking. Actually, tracking is about motion, object motion. Suppose you fix the camera, fix the camera, and object move. How can we track the object? That's tracking. The second thing is that if object doesn't move, you move the camera. That's also kind of tracking. Object doesn't move, but you move. So for if you do the stitching, pin tool, if you do the stitching also try to find corresponding point using SIFT, HOG kind of things. Also, you can use the optical flow. But SFT, actually, if you do the staging, find many corresponding points. One image, many points. Second image, many points. If you try to do the corresponding point over many points, SFT is better. But SFT is slower than optical flow. Optical flow is very fast. So optical flow is good for just part of the points. But if you have many points, you can use SFT. But as optical flow is very fast. So it's two kinds of motion. One is a fixed camera and object move. The other is a object move. Object doesn't move and you move camera. One problem is that if object move, camera also move. That's the problem. It's not easy to solve the problems. If both are moving, that's still a problem. So what's the optical flow? So suppose this is one image, and the second image here. So the car moved to here, the car moved, and this white taxi is moved to this one. You will see if we try to the over entire image, entire frame, and we see the flow between this flow, and we'll see some object moving here. So this one is the taxi, the white, this one, and this one is moving here. So we will see some motion here. So MPEG-4, MPEG-4. Okay, we do MPEG-4 is using optical flow. Why? Because if this one moving, we only need to save this image and save the optical flow. And we can, in the final one, we have the other image and we do the interpolation between the frames. Suppose this is frame 100, okay? And we have the other, and then continue from 100 to 110. And originally, you need to save 11 frames that occupy the memory. Now, the other way you can do is you just save first frame and save the last frame. So you only need to save 2 frames. And then you save the optical flow between 2 frames between them. And when you try to recover, and you can just use optical flow and between 2 frames and do interpolation. So that's an MPEG-4. MPEG-4 的压缩是用 optical flow 来做压缩的，但是它是 block 的压缩，这个我们就不提了。所以 optical flow 可以应用到很多地方。The other thing is that actually optical flow is actually displacement between 2 pages, right, in the two corresponding frames. 2 frames, if you have 1 page, you try to find corresponding point and corresponding page in the other frame. And this center movement between 2 frames is optical flow. Flow 是两个 frame 之间的物体的这个移动。But it's the velocity field. 它是一个速度哦，它不是一个 it's not a displacement， 它是一个速度量。But you say it's a displacement. Why is it velocity? It's because 2 frame is a time t delta t. So this displacement divided by delta t, that's the velocity. So optical flow is kind of velocity. 这很重要 ，optical flow 是一个速度量，不是一个位移量，因为它有时间轴，这样子。So up here on page 15. So optical flow related to spatial domain and temporal domain. 空间跟时间的关系。Spatial and temporal, I will explain this one. So why we need optical flow? And this is my research. 1993, I do this kind of plastic surgery. 做那个我在 CMU 做，我是最早做人脸表情辨识的啊，所以我事实上是人脸表情辨识专家。那受训的那个都，这不是随便就，因为要EMG要去 coding 这个脸部的 muscle 的移动，所以美国很严谨。那台湾很多人都做人脸表情辨识就是专家没有，只要是我们那个老师都去认证那个哪几个点是属于对的点，不能。那这个是 OK。So in the beginning, okay, we try to we work with the doctor in University of Pittsburgh Medical Center, UPMC, University of Pittsburgh Medical Center, plastic surgery. So he tried to measure the before his surgery, after his surgery, what's for the nerve, 像神经哦 what's difference. So he put the dots on the face, and then they ask the patient to the facial expression, and then they manually to detect to point the dot. 他们手去点这些点，然后就有 motion。那是他们那个时候这样做。So he asked my Professor Takeo Kanedi, my advisor. Optical flow is created by one of my senior students and then my professor. 这 optical flow 的发明是我老板发明，我那时候学长发明的，叫 LK 嘛 ，Lucas Kanedi 嘛 ，Lucas 是我学长。进去之后他毕业了啊，然后 Kanedi 他们发明的，所以他们。快10年前庆祝举办一个20周年的那个 LK 发明的一个发明的庆祝会，因为这个改变世界啊，包括之后我有个学长去美国是这样，我有个学长是那个军人，他是 MIT 毕业的 ，MIT 也是straight A 的学生毕业，然后他去当军人。然后来军人送他来我实验室做老板，来读博士。然后他当然学到这个 flow， 他说那时候他回来了，我跟他 overlap， 说他没用到 F16， 我们现在在用 F16， 那时候就 F4， 那时候他就有 F16的，是 F16 F15， 就抬头显示幕的抬头。那抬头显示幕也是，你看那个飞机啊。飞机那个先把物体那个对面的飞机先把它lock住嘛，另外一个绿色的东西这样过来就lock住，会追踪，就是他先锁定那个飞机，就这样找一直找，然后找到要锁定后lock住的话就跑不掉了。然后他说那有一部演算法是这个 optical flow 做的，但是世界上是3D， 所以它抬头显示幕那边是2D 嘛。但他是好像他没有讲明白，他是说有用那个雷射去扫描，然后然后有 optical flow 在那个抬头显示幕上这样去追。这个很快啊，这个你如果被 optical flow， 你只要被锁定，就是你用指头这样子画东西，画这个荧幕，这可以 optical flow 来做。然后我教你，那 OpenCV 有这个程式，因为我们作业会出这一题。好。我们回到这边 ，so we try to check the dots, and usually in the beginning I use this one. So this dots I use one template and trick and do NCC and do the tracking. But you'll find actually the dot because the face is 3D, you dots, right? So sometimes like in the cheek, this will distort， 就是那个 circle will become ellipse， 那个点是3D 的嘛，所以你这个点就不容易追。我那时候做这个，然后我and work really hard to do the tracking and work I think 1 month every day do this one. And my advisor, he never feel happy about this one. What I did is just okay. And each time when I do something better, he just said okay. And finally, after 1 month, 我是很认真在练读书。After 1 month, I feel I don't know how to improve this one because I feel this is good. I already did my best. And he told me, James, told me, do you know optical flow? I said, I don't know. I feel disappointed to you. 我对他认在内，他说他对我失望，我就做得很好，为什么你对我失望？搞不清楚。他就跟我讲啊，你是 you ask your senior student， 就问你学长，就跑去问学长，为什么我认真做了，我觉得已经做得很好了，吹很漂亮啊，这我做的。那时候做 real time， 都做 real time。我学长说，那老师说 optical flow， 不知道什么东西。他说哦 ，James， 笨笨的，这个 optical flow 那么有名，你还是我们这个实验室学长发明的，就跟我讲啊，赶快去看学长录，然后就去看录，就那学长 source code 在那边。我们有个好处是，我们实验室1980年的 source code 都一直存。我毕业的时候花3个月把整个东西博士东西整理完，才离开实验室，因为有那个传统，就一届一届传下来，花3个月。博士毕业花3个月整理完才离开实验室，因为以前的学长都把他的 source code 什么都整理得很好，造福后面的人。所以到我们目前我们实验室还有这个传统，只是我不能要求学生3个月，是尽量有好。那我就开始学 optical flow。那同时间不是我一个人做的，发现有。那为什么老板对我们失望是？他在教我们是说，你不能做研究，一个人在那边做不对，你要去跟人家问，看人家做什么事情。那么有2、3个学长都会做 optical flow， 这后面有改啊，改到有一个叫 structure from motion。structure from motion just meaning if you use one camera and just move, and you can become structure 3D. We call structure from motion. Structure is 3D reconstruction. From motion is tracking. Called structure from motion. 我在教 stereo 跟你讲的 structure from motion 就是这个。OK，so 我们有学长在做那个，他为什么做 structure from motion？ 因为 CMU 那个实验室 Robotics Institute 在1980年就开始做自驾车，所以我们落后他们很久。1980年实验室在做自驾车，然后1980年就在做 robot 的东西，所以 robot 它做 navigation， 它走出去，它开始辨识后面的物体，就 structure from 去用 STEM。我那时候是1999几年在那边，他们几年在做这些东西的，所以我回来台湾看到台湾做的都会做玩具，我们都做玩具。那他们在做什么？他们在做，我也搞不清楚他们要什么。那时候要做火星上的，所以我们那时候有大实验室，有很多学生在做火星上机器人，那个就是 JPL 跟我们实验室合作的。那有 stereo， 我有做 stereo， 然后我上是有做支架车，所以他们是真的。我们实验室有直升机，有军用的卡车，有军用的车子都有。UAV 都有，所以它是一个像是武器式的这样子。我们有卫星， 我们那个建筑物上面有那个大的那个雷达可以放卫星，前面看到哇，这边好像一个军中投资很多钱在那边大盘，发现哇，很多玩真的很有钱。然后回来台湾看到我们都在玩玩具，好，所以那个国内跟国外是投资的钱还是差蛮多的。回到这边，OK， so this is optical flow. What's the optical flow? So you think about, suppose we have a page here, and when you this mouth, when you open the mouth and the trachea to here, right? And from the starting point to the end point, in this direction, this vector, we call flow. This we call optical flow. So this template, and you open your moving from here to here, and this one, this vector we call optical flow. So how can you find this page in the second frame? This t and t plus 1. How can you find this point? Okay. And before we teach you is NCC, normalized cross correlation, right? So you have a search range, right? So if you try to find this one in this frame, you can search region, and you find the best match. So again, if you try to find a search region, that's 2D search. So in stereo, we try to reduce the 2D search to 1D search, and we base it on the epipolar line. Optical flow does not need to 2D search. He will track along the motion direction. Optical flow is not a 2D search. He will track along the motion direction. So that's why the fighter jet 那战斗机为什么要 optical flow 来做？因为它会沿着 motion 的那个物体的方向追踪它。它没有 2D search， 所以它是一个 amazing 的东西。它会只有沿一个移动的方向这样一直追过去。So so later I apply optical flow and for the motion, the facial expression recognition. So facial expression motion. OK， 这是轨迹的。这是下一个我就往 optical flow 去做去这些点。好，那我们看一些例子，先看we see some example of So when doing your homework, right? Your homework, each homework has a corresponding point, and you can find the corresponding point. Actually, that's the optical flow to the tracking. You track those points, individual point, just tracking as optical flow. So you do the calibration. Actually, you already use optical flow. The second one is your point. This is a trajectory. This is轨迹. So you can check this one. And actually, you do the motion. This can do 3D reconstruction. I say structure from motion. 你只要这样移动一下，3D 就可以逐渐出来。那时候是吴老师他做的，我博士研究。Okay, and this is what I did. 这是我的博士论文。我们以前毕业都要做一个 user interface， 要求学生一定要做成 video。这是1998年做的，追踪小孩子 facial expression。这是在 Linux 下面的，那时候 Unix workstation 下面做 trick 小 还是 beauty。所以我们的表情不是只有喜怒哀乐表情，是做到这种细致的表情，这都要分析出来。上有 flow， 这都是心理系的学生。我们做这个要跟心理系合作。美国很专业啊，当时心理系的学生，他100多人修那门课，有来做表情的就加分这样子，然后再收集他的资料。我那时候自己忘记做表情。那个 UPIT 的匹兹堡大学的那个心理系好像全美第2名这样子。他们心理系怎么样啊？这是我以前做的。那这是 this is a 这个，所以 this animation 这是很久以前做的，那个现在都3D 的嘛哈，现在有那个defect 嘛 ，defect 变相，那我们是做这个好玩的，用这个人脸控制这个人脸。那 inside this one is the article. We use this face to control this face. 这很久以前。So this is optical flow application. 再来看一些，那这是也是我以前一个博士做的。再用一下。Use optical flow, this optical flow here, and they can use 2D control 3D. We can use 2D optical flow control 3D. 所以那时候我们实际上有做这个，那时候还没有 deep learning 的时候有做这些。我们再继续看一些东西，看一些应用。那这不是 optical flow， 这 the other kind of tracking. So if the target is bigger, don't use optical flow. It'll be slow. 这是另外一种 tracking 的方式 ，track 这些，这车子的 tracking， 所以是 kind of is tracking， 这是另一种 tracking。后面有点，这点是 not affected by occlusion, but here will affected, will be affected。到时候会有人问。失败了有没有？所以有成功有失败，这不受光线影响。看一些应用。那我们专题生，我那是专题生，我教他用这个。这是 optical flow because it's a small， 这很久前做的，这是学长做的。这个没写几年，很久前做的。这种 YouTube 上面 trick。Small object can use optical flow， 所以那时候 optical flow 追这个要求。所以我们很早，这10几年前，我们早就分析这种棒球规则。所以我最近看到台湾做了很多这种东西，这个是落后美国大概是30，我觉得台湾技术大概都后面走15年了，但是没有什么不好的，因为台湾很会 cost down， 因为美国这个都很贵，做这技术那转播一场可能要付科技公司100万美元啊。台湾厉害是 cost down， 所以我们工作都很辛苦，就是把球贴回来。 我们把球贴回来，so you can see the trajectory。这都 real time tracking optical flow track， 专题生一个系统，这专题生组。那对棒球都是细的棒球本。好，这当然让你知道一下有这些东西。再大家看一下那个 optical flow 的其他应用。那这个是 stabilization， 是这是 optical flow 做的，是晃动的这个。in reality 是这个，啊，实际上做出来变成这样 real time 的不动。这我们实验室做的，所以我们实际上测试 ADAS 做很多，那时候跟美国、德州一起合作，可惜最后没有商业化。这是手机拍的，这是 stabilization 后的结果。这我们也做得很好。美国德州其实我看过最好的运算法是这个，就这个移动。我可以把它静止不动，就做的非常。stabilize， 再看一遍这个，移动那么大，这都不动，所以我们可以做上 stabilization。那大概这样让你了解这个可以做这些东西啊。Back to here， so optical for a lot of application。那我跟你讲说 ，optical flow is they include spatial domain and temporal domain。这例子你自己看，开始解释 optical flow。So there's Lucas Kennedy， we call Lucas Kennedy LK optical flow。Lucas 就是我学长 ，Kennedy 是我老板。So suppose in this one, from t to t plus, and this one is the gray value. So this is time. So this gray value. So from here to here, this gray value here. Okay. In the t plus 1, in the same line, the gray value is here. So the purpose for optical flow you will find, they will track from here, track to here. So this is the flow. The move, the displacement, and how can, so in mathematics, so original is IT, the position is supposed X, and X suppose is belong to some region. So in this case, the suppose R is belong to a small page. This we just pick up, suppose pick up one point here, so this one small page。把它当成是这里有个，这个啊，就假设这有个小的 page 在这里，小 page。这个 page 会 track to here。那假设这个 page 是11 by 11 page，那意思就在这里就是一个小段，这有个小段在这里，从这一段你要追到这一段。This is U displacement U. So that's meaning in xt, suppose the center is x, centered in x, and the movement between two is a U. It's 1D case, suppose 1D case. And how can you find U? U is not U. So it may make it this way. Similarity, right? In t plus 1, the pitch will be here. In t, pitch will be here. So between, suppose this one, if this one's here, become here, right? 这个在这里虚拟的前一个 frame。那这个位移就是 u 嘛。So how can you find u? So u is the optical flow. So how can you find it? So you want to minimize this error, right? Because the picture is the same. Small page, 11 by 11. So let's cost function or loss function, the same loss function. And you try to minimize the loss function in order to find u. In 2D case, this is small page. Right? And in t plus 1, you move to here. So this direction, this vector, is u and v. It's u and v. It's 2D case. Suppose this is also 11 by 11. You try to minimize this one in order to find u and v. So optical flow, the equation of optical flow is very simple. It's easy. You just try to do optimization for this one. And I don't, this is, you do it read by yourself. So in 1D case, how can we solve the u or h? Here we say h. This h actually is this u, the same, the displacement. And his minus and his plus, actually the same, just direction difference. It's a vector. So plus is meaning minus minus 负的方向，所以实际上是只有方向不一样，所以是一样。So how can we minimize this loss function in order to find the displacement h? So that's optimization. So that's SSD problems, right? We find how can we solve SSD problem? So we teach you before we teach you we have this kind of method, right? 之前有教你教过。在这里，你要 optimization. How can we do this one? So again, this optimization method. So Lucas think about, okay, this just straightforward. 这是他发明的 straightforward. We try to find h. So the easy way, the same as the gradient descent, we derive by the h. 我们要找什么就跟做微分，也就是二次项。我们要找什么就对什么做微分，所以就对这个 h 做微分。那 h 做微分，这我写的啊，就把2提出来嘛，然后保留住。那再把因为这个 h term, so we derive by this term. So this is equal to 0. Right? So we minimize, we try to find the point here. 这是二次曲线，那找最小值，找这一点，这一点是 h。就这个如果是这样，这个如果是方向这样，那你就要找这个 h 值，这一点最小值。这是 error term 最小的 h， 找最小值 h， 所以你要找 h 就对 h 做微分。那再怎么做？所以你有时候看到，哎，这个看好你像你也会做，对啊，但是我们都没有想到。所以学长就说，哎，我用 first order Taylor series。那 Taylor 是这样的嘛 ？x plus h， 因为 our purpose is try to find h, so we try to separate the h. 你要找什么就把那个东西要提出来，所以我才有 separate the h， 所以它用一阶微分来做。那我们就这个就变成这个一阶就 ix plus this one. So we again for hix plus h term we input here. 所以 ix plus h 就被这个就被取代掉了，这个就被取代掉了。那这个就 ix plus h 这个被取代掉了，就把它取代掉。但记得这是 approximate， 这是接近、逼近。这个式子 h 就提出来了 ，h 就可以提出来，然后再整理一下，就最后变成这个式子。这个式子我们再重新intermediate嘛，重新整理就变成这个式子。那 h 在这里提出来了。然后就把 h 提出来，这是结果了。这样子 ，so we will find out this is result here. So result is this one. This is denominator term， 就是分母的 term， 就是 I 对 x， 因为 this is 1D， 所以是 derivative of 1 derivative 2， 是 two derivatives。这是一次微分，那是相近。This is actually this is f what's f? Sorry, this is suppose this t plus 1 and this t, this template, this t and this t plus 1. So this is the difference between two. So actually this is the derivative of 2. 这是微分啊，相减就是微分。这是二阶，两个一阶啊，你看这里两个一阶，所以这是 denominator term the sense denominator term， 那你把两个相，因为这两个二一阶，两个一阶是这是 constant term， 就是这种常数项，这是合理。假设这是一个微分，这两个微分，你出来就会一定要一个微分项这样子。但是 this is both the derivative, so this will be constant term. So that's your answer. So what's your answer? Your answer is in the denominator term. This is x derivative. In the image, the derivative along x direction. This is a 1D case. So only 1D. So u is x. So this is along the derivative. So actually this is h detection. The h in one direction. This h in one direction. And this difference between two edges. So actually try to minimize this one. Right? If they both are the same, that means the page will match the result. If both are the same， 这两个相同就是 match trick。好，我老板跟我们讲这个故事，我老板说 I'm tough， 他很严厉，是他很严厉，他笑的很严厉对学生，要求很高。学长这样做出来，发明出来的不满意，因为这个是一个 ，this is approximate 就是逼近的 ，this is not equal。So this meaning this result should not be equal. So what can you do is that you need to do the iteration. So you have iterate. So why is the gradient descent need to do the iteration? 因为你要去一直逼它到它收敛为止，这样子。记得，我待会再继续讲这个，就是说，因为这个不是等式，是估计值。那你要达到等式的话， 一个方法就是一直 iteration 去逼它，逼到它收敛为止。这是 attenuation 一个常会遇到的问题。OK， 好，那 we will take a break and then we will continue. Take a short break.